Good day, everyone. Today, we are honored to present our research on the global risk factors and the epidemiology of lung cancer, focusing on a comparative analysis across 25 countries. This study aims to uncover key contributors to lung cancer prevalence using data driven approaches and statistical analysis. Before we begin, allow me to introduce the members of Group 7 who have collaborated on this research. Bianca Ala Ocampo, Ara Ortega, Robert Tin, Kev Pabunan, and Calvin Fersidanga. Each of us played a crucial role in analyzing data, interpreting results, and drawing meaningful conclusions about lung cancer risk factors worldwide. With that, let's proceed to the abstract of our research. Good day, everyone. Today, we will be discussing one of the deadliest diseases worldwide, lung cancer. Lung cancer remains a significant global health concern, with smoking, secondhand smoke exposure, and genetic predisposition being the primary risk factor. In our study, we analyzed lung cancer prevalence across 25 countries, using machine learning and statistical methods to determine key contributors to the disease. By utilizing the dataset from Kaggle, we examine correlations between smoking habits, public health policies, and socioeconomic conditions in lung cancer incidences. Our predictive model, developed using a random forest classifier, achieved a 100% accuracy, highlighting the strong influence of smoking related factors. However, our research also underscores the importance of external validation and the need to include additional variables such as environmental pollutants and occupational hazards. Our findings emphasize the necessary for stricter tobacco regulations, improved screening programs, and the adoption of advanced data-driven healthcare strategies. This studies highlights the role of machine learning in public health decision making and calls for proactive interventions to mitigate lung cancer risk worldwide. Before we dive um, into our research, let us first establish the background of our study. Lung cancer is one of the most fatal types of cancer, accounting for approximately 1.8 million deaths per year. According to the World Health Organization, the leading risk factors include smoking, exposure to secondhand smoke, and genetic predisposition. However, lung cancer rates vary across different countries due to public health policies, smoking habits, and environmental conditions. With this in mind, our research aims to explore how these factors contribute to lung cancer in incidence and how data science can be utilized to analyze and predict trends in different regions. Lung cancer remains a pressing global health issue. The disease is primarily caused by smoking, but other factors such as passive smoking, occupational exposure, and genetic predisposition also play a role. In many countries, government policies regarding tobacco control and early screening programs differ, leading to variations in lung cancer prevalence. Understanding these differences can provide insight into the most effective strategies for combating the disease. This study leverages data science techniques analyze lung cancer risk factors across 25 countries, offering a data driven perspective on a public health interventions. Our research focuses on understanding lung cancer risk factors by analyzing data from multiple countries. We examine the impact of smoking prevalence, passive smoking, family history, and healthcare policies on a lung cases by applying machine learning techniques. We identified key contributors and assessed the effectiveness of tobacco control measures. Our study aims to highlight how data-driven strategies can enhance lung cancer prevention and intervention efforts. Ultimately, we advocate for stronger regulations and more comprehensive screening programs to mitigate lung cancer risk globally.
Now, moving on to the importance of the study, we have already established that lung cancer is a major health concern globally, with its high mortality rate making early detection crucial. Various factors influence its prevalence, including genetics, lifestyle choices, and environmental exposure. By leveraging data science and machine learning, we can uncover significant risk factors and develop predictive models that can assist in reducing the impact of this disease. Early detection and risk assessment can save lives by guiding public health policies and prevention strategies. Machine learning offers a powerful approach to analyzing risk factors and predicting lung cancer incidence. Next, we have the objectives of the study. Our overall goal is to determine the key risk factors associated with lung cancer and how they vary across different countries. But specifically, we want to identify the strongest risk factors for the lung cancer by analyzing the correlation between smoking habits, passive smoking exposure, family history, age, and gender. Next is to compare lung cancer prevalence across 25 countries to assess how smoking rates, healthcare policies, environmental factors, and socioeconomic conditions influence lung cancer risk. Also, we want to quantify the impact of secondhand smoke exposure on lung cancer risk compared to active smokers and non-smokers. Lastly, we want to utilize machine learning models to develop predictive insights into lung cancer risk factors.
Before we take a deep dive into the methodology we applied to our dataset, let me first discuss existing studies and related literatures related to our research. In the context of lung cancer research, advances in data science have greatly enhanced early detection, diagnosis, and prognosis, all contributing to offering life saving insights. Kadiri and Gleason demonstrated the power of convolutional neural networks or CNNs in classifying pulmonary nodules from CT scans, achieving over 90% accuracy. They emphasized the importance of high quality training data in patient history, showing that these models can be integrated into clinical decision making systems like CADX. Similarly, Kwan et al. Developed a multi stage deep learning framework capable of detecting lung cancer in 3D CT scans, highlighting the potential for early diagnosis and the adaptability of these methods for other cancer types. Beyond detection, understanding risk factors is vital. Albert et al. Identified key risk factors including smoking, secondhand smoke, air pollution, and occupational carcinogens. They stressed that risk prediction models need refinement, a challenge that machine learning can address by identifying complex patterns in risk factor interactions. Chen reinforced this by linking historical tobacco consumption to current lung cancer rates in Canada, Norway, and Sweden, emphasizing the potential for data science to guide population level interventions. Barta et al. Expanded on this by analyzing global lung cancer trends, revealing how smoking habits, environmental exposures, and healthcare infrastructure can influence regional variations in incidence and mortality. These studies collectively illustrate the enormous potential of machine learning to enhance both clinical practice and public health strategies through more precise detection and risk assessment. Shifting our focus to public health and policy, it becomes clear that machine learning is not only a tool for clinical detection, but also a powerful asset in addressing broader healthcare disparities. Lee et al. Highlighted the persistent burden of lung cancer in developing nations, attributing this to weaker health policies and inadequate screening programs. They argued that machine learning offers a cost effective and scalable solution for resource limited settings capable of incorporating socio-economic data to guide more equitable healthcare interventions. Similarly, Paksad et al. Explored the link between lung cancer rates and development indicators across Asia, showing that environmental exposures and economic development both play critical roles in disease prevalence. Their findings suggest that machine learning can facilitate a more holistic understanding of lung cancer by processing diverse datasets, ultimately aiding policymakers in crafting targeted strategies for high risk populations.
Let's talk about the methodology of the research. Our conceptual framework illustrates the relationship between the various factors that contribute to lung cancer and the following effects. When we are talking about the independent variables, these are the important external risk factors affecting lung cancer development. The moderating variables are factors such as the prevalence, the number of years, and the number of cigarettes smoked per day affect the intensity of lung cancer. Next, the main dependent variable is lung cancer, with several subcategories of other dependent variables. And lastly, the meditation variable connects the dependent variables. Here are the ergonomic tools used in the study. Our study utilizes Jupyter Notebook as the primary tool for live coding, data analysis, and visualization. It allows seamless integration of code, documentation, and statistical insights, making the research process interactive and efficient. The Python libraries used were Pandas for data manipulation and cleaning, NumPy for numerical computations and array-based operations, SciPy for advanced statistical analysis, Matplotlib and Seaborn for data visualization, and lastly, scikit-learn for machine learning for predictive modeling and pattern recognition.
Now let's walk through the statistical methods we applied to analyze lung cancer risk factors and build our predictive model. This process was divided into four phases: data cleaning, data exploration, data modeling, and model evaluation. We began with data cleaning to ensure accuracy and consistency. The dataset was checked for duplicate rows and inconsistent categorical values. We removed unnecessary columns like patient IDs to streamline analysis. Additionally, categorical variables were converted to category types for memory optimization, improving processing speed. Next, we explored the data using descriptive statistics and visualizations to uncover initial patterns. Histograms reveal distributions for age, smoking status, and lung cancer diagnosis. We visualized categorical relationships through stacked bar charts, highlighting the proportion of smokers, passive smokers, and individuals with a family history of lung cancer. A Pearson correlation heat map helped us quantify the strength of linear relationships between variables such as cigarette smoke per day and years of smoking. To deepen our insights, count plots and bar graphs illustrated how lung cancer prevalence varied by gender and smoking status, giving us a clearer picture of potential risk factors. Building up on our exploratory findings, we developed a predictive model using a random forest classifier. This model handled both categorical and numerical features, making it well suited to our dataset. We then applied label encoding to convert categorical variables into numerical representations and z-score normalization to standardized features, improving our model convergence. And since our dataset was imbalanced, we used synthetic minority oversampling technique or SMOTE to generate synthetic instances of the minority class, ensuring that the model learned from an equal representation of positive and negative cases. The data was then split into 80% training sets and 20% testing sets to assess generalizability, and we trained the random forest model using 100 decision trees with a fixed random state for reproducibility. For evaluation, we relied on multiple metrics. Specifically, accuracy, precision, recall, F1 score, ROC AUC score, and a confusion matrix. The model achieved 100% accuracy with perfect precision and recall, meaning that it correctly classified all test cases without false positives or negatives. The ROC AUC score of 1.0000 indicated ideal discrimination between classes. But although these results suggest a highly effective model, future validation with external datasets or cross validation would further confirm robustness.
Here is our results. First, before our results, we did our data cleaning, which allows us to check the dataset for inconsistencies and remove some of the columns that were not relevant in our project statement. For our exploratory data analysis, our dataset shows that smoking behavior shows an average of 8 years and around 7 cigarettes per day. Lung cancer prevalence rate averages a 1.52 with notable variation, and mortality rate has a mean of 3.95 but high variability. The age distribution of our participants show a diverse range starting from 20 years old to 80 plus. However, the majority of the participants do not have lung cancer, but a smaller portion has been diagnosed. For our correlation heat map of numerical features, the Pearson correlation shows that strong correlations were found between smoking habits, mortality rates, and lung cancer prevalence. The color red indicates strong correlations like years of smoking and cigarettes per day, while mortality rate and annual lung cancer deaths reinforce known risk factors.
Lung cancer risk factors. This slide presents three bars showing lung cancer diagnosis in relation to smoking, passive smoking, and family history. In all three cases, we see a significantly higher number of lung cancer diagnoses among individuals exposed to these risk factors compared to those who are not. This highlights the strong correlation between smoking, both active and passive, as well as genetic predisposition and lung cancer occurrence. Lung cancer diagnosis by gender. These bar charts compare lung cancer diagnosis across genders. While the number of diagnosed cases is slightly higher in males, the overall trend remains similar for both genders. This suggests that while gender may play a role, other factors such as smoking habits and genetic predisposition are more influential. Data modeling. Confusion matrix for data modeling. The confusion matrix displayed here that shows our random forest model achieve perfect classification with no false positives or false negatives. Key performance metrics include an accuracy of 100% and an ROC-AUC score of 1.0000. This suggests that the model effectively distinguishes between lung cancer cases and non-cases. However, while these results highlight strong predictive power, they also raise concerns about potential overfitting. The absence of misclassifications may indicate that the model has learned data specific patterns rather than generalizable trends. Model evaluation, confusion matrix for data evaluation. In summary, the random forest model demonstrated exceptional accuracy, outperforming alternatives like logistic regression and decision trees. However, further validation is needed using external datasets to confirm generalizability. Comparing performances with simpler data models could also help determine whether random forest complexity was necessary. Additionally, our findings reinforce that smoking and passive smoking are significant predictors of lung cancer, aligning with medical research. Moving forward, refining hyperparameters and testing against real world data will be essential to ensure robustness and reliability in practical applications. Conclusion. The study analyzed lung cancer risk across 25 countries using data science and machine learning, confirming smoking as the leading cause, with secondhand smoke significantly increasing risk. The random forest classifier achieved high accuracy and risk prediction, while variation in prevalence highlighted the impact of public health policies, culture and healthcare access. Data limitations restricted deeper analysis of genetics, environmental factors, and occupational hazards. Strengthening tobacco control, smoking cessation programs, and personalized risk assessments is crucial for early detection and reducing lung cancer's global impact.